Okay, it sounds like a lot of you have finished. So this will give us a little bit more time to go over the answers, right? So let's start. Now you've done them, so what I'm going to ask you for the voting system is you'll have just 10 seconds to write the answer that you put down. So this is for question 1. Let's have the voting. These formulae were in that document that you should have received in the PDF form for the Pacemaker Basics with all the formula. Okay, interesting. So you'll have here the correct answer. Most of you got it right. 10 milliamperes. That's the formula, Ohm's law, V equals IR, and mathematically this is what you get. The difficulty is sometimes also having the units. So there's something you have to always be very careful about, the conversion factors. So most of you got that right. So I think we'll move on to the next question. Which pacemaker will last longest? So open the voting. Okay, so that's a bimodal distribution. And the correct answer is D. So as you know, the amplitude is very important for the pacemaker longevity, right? Because the energy is proportional actually to the square of the voltage. It'll also depend on the pacing rate and the percentages of pacing, but they're all pretty similar. And of course, lead impedance. The higher the impedance, the lower the current drain. But the combination which gives you the longest longevity is D. Okay, question number 3. On the strength duration curve, line 1 is, line 2 and point 3. So we'll start the voting. Okay, so these are relatively basic concepts. The proper answer is B. So line 1 is the Rio base. The Rio base is the capture threshold in terms of amplitude that's at infinite pulse duration. Now, in practical terms, this is usually measured with a pulse duration of 2 milliseconds. Okay, because as you increase more than 2 milliseconds, you're not going to change very much. You can see that the curve really flattens out at 2 milliseconds. So this is the Rio base, first one. This here is twice the Rio base. Now, I see that a lot of you actually gave answer C, which means that you think that this is chronaxy. So chronaxy is because of chronos is time. So chronaxy would be this here. It's the stimulus duration at twice the Rio base amplitude. It's a bit of a tricky question. Oh, it's different in the printout. Okay, so sorry about that. Okay, that's strange, but anyway. So I guess that's perhaps what explains the difference. Fair enough. And the third is the point of minimum energy, which is true for both of them. Okay, so it's a question of arrows and interpretation of them. Good. Okay, so we've talked a lot about PMTs today, so I hope that you'll all get this right. So let's vote. Okay. So, right, answer number 3. Right, so indeed, ventricular oversensing, and the trap here is that may result in PMT, except, okay, so ventricular oversensing will not. Good for that. All right, so other causes of PMT, we've covered them today. Atrial non-capture, very long AV intervals. Okay, question number 5. What do you see on the following EGM and marker channels? So go ahead and vote. Okay, so good, 73%. That's pretty straightforward. You can see the atrial pacing, and you still have the atrial sensing behind, so very clearly loss of atrial capture. Okay, next one. ventricular pacing at a rate below the lower rate limit may be caused by the following, except, go ahead and vote. A, hysteresis, B, T-wave oversensing, C, rate drop response, or D, auto-sensing algorithms. Okay, again, about half of you got it right. Now, a fair amount actually got the wrong answer, so I think we'll try to go wise. So obviously hysteresis, 18% of you thought that hysteresis would not give you longer, a slower rate. Well, that's the aim of hysteresis. If you program a lower rate at say 60 beats per minute, and you have a hysteresis at 50 beats per minute, it will allow the rate to come down to 50 beats per minute. Okay? Okay, right. Okay, that's true. Ventricular pacing. I think I take that ventricular pacing at a rate below the lower rate limit may be caused. Okay, so actually the wording should be a little bit different. It will allow the heart rate to be below the lower rate limit, and it will pace at the lower rate limit. Fair enough, but you sometimes have situations where you're hesitating with the two. You should take the one that is more likely to be wrong. So rate drop response, there's no reason why rate drop response should allow you to pace below the lower rate limit. It's just a sort of a rate, when you have a very fast drop in heart rate, such as in vasovagal syncope, it's going to be pacing at a high rate to try and counteract vasovagal syncope. So that is the most wrong answer. But I give it to you if you're quite right that, to be very specific, I think hysteresis could also be wrong. Otherwise, T-wave oversensing, that's a good reason why you may sometimes have ventricular pacing at a rate that's lower than the lower rate limit. You should always think of T-wave oversensing. And well, auto-sensing algorithms, what they do basically is that they try and promote as much as possible the intrinsic rhythm to look at the intrinsic activity, be it atrial or ventricular. So that's where you may have, during very short periods of time, very low pacing rates. Okay? The next question, what's the initial voltage of a pacemaker lithium battery? Go ahead and vote. Okay, well, most of you got that right. It's around 2.8 volts, roundabout. 2.5 volts, 16% of you thought 2.5. That's usually at end of life already. So, and 5 volts, no, there's no pacemaker that has a battery at 5 volts. Okay, so the next question. All of the following are necessary to maintain a pacemaker endless loop tachycardia, except, go ahead and vote. Okay. That's good, 75%. There was a little, that's the correct answer. The little trap there is the maintain. This is where little words can make a big difference. And the premature ventricular contraction can initiate a PMT, but it's no longer necessary to maintain it. Well, most of you got that right. Very good. Okay, next question. What do you see on the following EGM and marker channels? Go ahead and vote. Answer 3. That's correct. So there are a lot of things. It's a very busy tracing, but you do see ventricular undersensing. This is the ventricular electrogram, and there is no R annotation here. This ventricular beat is clearly undersensed, and you have ventricular pacing, and far field R wave oversensing. That can also be appreciated. Let me just check here, for instance. You have a ventricular beat that's being actually sensed far field in the atrial channel with relatively high far field R wave. So this is something which at device implantation you should always look out for when you place the atrial lead. Look out for these high amplitude far field R waves because you really don't want to have them. They'll lead to all sorts of problems later on. We spoke a little bit about that earlier on today. So the next question. A pacemaker's low rate is programmed to 60. The interval time between pace beats is 1,000 milliseconds, and the interval time between a sense beat followed by a paced beat is 1,200 milliseconds. This could be due to, go ahead and vote. I hope to see 100% on this one. 90. Okay, so 88.6 got that right. So this is indeed hysteresis. Okay, it'll allow, the base rate is 60, it'll allow to come down to 50 beats per minute as long as it's sensed. And at 50 beats per minute, it'll start pacing at 60. So that's hysteresis. Okay, it's something you really should know. Okay, next question. The purpose of the ventricular refractory period is, go ahead and vote. Okay. To prevent timer reset of the T wave, that's perfectly correct. So that's the ventricular refractory period. It's very unlikely that intrinsic atrial signals get sensed in the ventricle. Very, very unlikely. There's certain circumstances when this can happen, but it's extremely unlikely. So it really is due to prevent timer resetting of the T wave. Okay, now it has nothing to do with promoting intrinsic conduction, and we're talking about ventricular refractory period. Okay, so, and this would not be atrial refractory period. Good, so most of you got that right. Next question. Going back to some physics again, for the voltage of 5 volts, resistance of 500 ohms, and a pulse width of 0.5 milliseconds, calculate the energy delivered. Go ahead and vote. Okay, so bimodal again, answer 3 and 4. So the answer is 25 microjoules. Now, how do we get that? So if you remember your formula, energy is voltage squared times time divided by resistance. Okay, that's the concept you need to know, and that's why it's very important the amplitude, the pulse amplitude you program for pacing. Okay, that's something which is going to influence considerably the device longevity. So here you have, we set the voltage of 5 volts, 5 squared is 25, times t, and now we're talking about milliseconds. So 0.5 milliseconds is 0.5 divided by 1,000, divided by the resistance, which is 500 ohms, and this will give you 25 times 10 minus 6 joules, or 25 microjoules. So what do you see on the following ECG? Please vote. Okay, good. That's good. So what you see is there's atrial pacing at a constant rate. Obviously, the pacemaker is not going to respond itself to carotid sinus massage, so there's no slowing of the atrial rate. And what you see is blocked P wave here, atrial pacing with no QRS. Here a long AR interval. And what happens is you get consecutive beats which are blocked, and the device then switches to ventricular pacing, because you can see that the QRS complex is of different morphology compared to here. And the AV interval is also a lot shorter. So that's correct. Sinus carotid massage, switch from ADI to DDI. Incidentally, you've seen that a lot of these pacemaker algorithms, they call them AAI DDI, which technically is wrong, because the true functioning mode is ADI. AAI means it's not sensing at all in the ventricle, and it is sensing. So it's pacing in the atrium and sensing in both chambers. Okay. Next question, what do you see in the following EGM and marker channels? Go ahead and vote. Okay, so it's divided between answers 1 and 2. So the correct answer is A. Technical loss of atrial sensing and atrial contractions are inside atrial absolute refractory period. You see, you have ventricular sensitive events, you have a lot of atrial events. The patient's obviously in AFib. A lot of these atrial events are being sensed, but from time to time, there is a loss of atrial sensing. For instance, here, you can see that there's no AR here, simply because of the ventricular sensing, and there is an atrial refractory period which is therefore technically not, the pacemaker is technically not able to sense the atrium. Okay? It hasn't prevented the device from mode switching and from working properly, but you do see some atrial events which are simply not sensed because of that ventricular refractory period. Okay, so B is not wrong, because it's true, some atrial contractions are not detected, but A is a more correct answer. It's more complete. So that's why A is the correct answer here. This would be an absolute refractory period. If it's a relative refractory period, it would be AR. Okay? It's in the refractory period, it's detected, but it's labeled as AR. So it is in a relative refractory period. The fact that you don't see anything at all means that it was in the absolute refractory period or blanking. The only device where you would see something marked there would be in a Medtronic device, in more recent devices which are built on an ICD platform, where you would see AB, or atrial blanking, actually shown there. But normally atrial blanking means that the device, it does not even see it. It's a bit of a particular, something a bit specific for that device. Next question, ventricular safety pacing. Go ahead and give us your answers. Again, I hope for close to 100% on this one. Not bad. 88. Good. Satisfied with that. Indeed, protects the patient from the ill effects of crosstalk. Okay, what you don't want is atrial pacing with the spike to be detected in the ventricular channel, thereby inhibiting ventricular pacing, because if the patient's in complete AV block, well, he's in asystole. Good. Next question, what do you see on the following EGM and marker channels? Okay, so answers 3 and 4. The correct answer here is answer 3, junctional tachycardia. So this is a little bit like EP. On this device, you have the atrial and ventricular EGMs, which are on the same channel, which is sometimes a little bit confusing. But what you can see is you have P and V, that means atrial sensing, ventricular pacing, and it starts off with a P, a premature atrial beat. One premature atrial beat with intrinsic conduction, because you have an R, a second atrial premature beat with intrinsic conduction, and then what you see is at the end of, just after the R, you have a little spike there, which looks like, in fact, an atrial sensed event, is not seen here, and is seen intermittently thereafter, because it is so close to the R. And this is why you always have to look at EGMs, and not just look at the marker channels, because the marker channels tells you what the device is seeing, but doesn't necessarily see everything. But you clearly can see an atrial sense here after an atrial event detected, an atrial event that should be detected after the ventricular event. So basically you have two atrial premature beats that then set off AVNRT, or junctional tachycardia. Yes? We just have one question, I'll come back to you. Yeah.
The morphology of the EGM of tachycardia is completely the opposite of the before.
So these are actually, you're talking about the ventricular EGMs. This is ventricular pacing, it's V, and this is R, ventricular sensing. So obviously the EGMs are going to be different. You had a question as well?
Yeah. How can you prove it's not ventricular tachycardia?
Okay.
Supposed to be very irregular.
Yeah. I cannot prove it, but it's highly likely because your tachycardia starts off with an atrial event. Okay, and this is sometimes what's used by ICDs. They see, where did the tachycardia start? It started in the atrium. Very clearly, you have this is sinus, and then you have two premature beats that then set off the tachycardia. The second thing which would speak against ventricular tachycardia with retrograde VA conduction 1-to-1 is the fact that the VA interval here, or the RP interval, is relatively short. If you have ventricular tachycardia, you would expect it to be somewhat more long. Okay? It's in fact so short that sometimes it's not seen by the pacemaker itself. Right? Any other questions? Good? Was a tough question. Okay, next one. Which definition corresponds to the interval marked in the drawing? Please vote. So we have this in the dark following an atrial paced event. Okay, right, so most of you got that right, but still about over a quarter thought it was just atrial blanking. Now, atrial blanking is correct, atrial blanking, but this is more correct. It's post-atrial ventricular blanking. It's in the ventricular channel. So atrial blanking actually, sorry, would be wrong because it means that you're actually blanking the atrium. Here, it's in the ventricular channel and following an atrial paced event, okay, to prevent crosstalk. So PVAB, post-atrial ventricular blanking, PAVB, post-atrial ventricular blanking. Any questions on that? Okay. Next one, a DDD pacemaker recognizes which of the following is a PVC? Please vote. Okay, so it'll be between answers 3 and 4. The correct answer is sinus beat with atrial undersensing. Basically, for a pacemaker, a ventricular premature beat is a ventricular sensed event that's not preceded by an atrial event, either atrial paced or atrial sensed. Okay? So it may be either atrial sensed or atrial paced. Ventricular sensed event. So the only thing that can do that here is a sinus beat with atrials undersensing and of course conducted AV. All the rest, in fact, will not be classified as a PVC. Any questions on this one? Good. Next question. This ECG was recorded from a patient with an AV block who received a dual chamber pacemaker. Programmed basic rate was 60. The patient came to scheduled routine follow-up. What are your observations? Please vote. Okay. Answer number 3 is correct. Ventricular safety pacing. What you see here is a P wave, normal P wave, no spike, and ventricular pacing, atrial pacing, ventricular pacing. And here, visibly, there is atrial undersensing, but this is not part of any of the answers. You have ventricular undersensing, but this is atrial undersensing. Atrial pacing, okay? Now, what happens is, because this P wave was not detected, and because there is intrinsic AV conduction, and because you have this atrial pacing, this ventricular sensed event, this QRS complex is sensed. How do we know it's sensed? Because you have suddenly a shortened AV interval. You see this AV interval here, or this one here, is a lot longer than this one. And this is actually 110 milliseconds, and this is indeed ventricular safety pacing. So most of you got that right. And you have it again repeated here. Okay, very good. 20, what happens in this tracing? Please vote. Okay, that's good. So we're close to 100%. You've made me very happy. That's good. No need to go any further on that one. 21. The principal purpose of the PVAP in the dual chamber pacemaker timing circle is to prevent which of the following? Please vote. Good. Okay, so atrial sensing after retrograde conduction. I think most of you got that right. So 17% still said atrial sensing of the ventricular pacing stimulus. That's actually, that would be the ventricular blanking you're thinking of, the post-ventricular atrial blanking. That was what you're thinking of, but we're talking about PVAP. Okay? Next question. A dual chamber pacemaker is programmed to basic rate of 50, AV delay post-atrial pace 200, sense compensation 50, PVAP 250. What's the maximum programmable tracking rate? Please vote. Okay, there's a bit of a spread. That's good. Most of you got it wrong actually here because it was 120. Now, there's a little trap there, and I think most of you probably got this wrong with the sense compensation. The sense compensation is the difference between the paced AV interval and the sensed AV interval. In general, the paced AV interval is longer than the sensed AV interval because the sensed AV interval, in fact, the atrial sensing by the device occurs within the P wave. The P wave has already started. By the time the depolarization gets to the atrial lead, the P wave has started already. Whereas if you have atrial pacing, that truly is the beginning of the P wave. Now, the other thing is you have to remember is that maximum tracking rate, in fact, will depend on the total atrial refractory period, TARP, which is the AV interval plus the PVARP. Okay, so the AV interval here is 200 minus 50, which is 150, plus the PVARP 250, gives you 400 milliseconds. And if you want to convert intervals to rate, it's 60,000 over 400. It gives you 150 beats per minute. So 1/5 if you got that right. But there was a little bit of a trap in there, so I think that's probably why you got it wrong. Okay, next question. Which of the following is incorrect? Please vote. It's a bit of a toughie, this one. Okay, well that's good, actually. Most of you got it right. I'm pleasantly surprised. Now, the question is, why is the ventricular refractory period shorter than the PVARP? There's a reason for that. If it is shorter, if you have a ventricular premature beat, you may have far-field R-wave oversensing. That can happen, right? Now, if the far-field R-wave oversensing occurs within the PVARP, it'll be classified as AR and will not reset the timers, notably the AV interval. If the contrary were true, that's to say the PVARP were shorter than the ventricular refractory period, if you have a ventricular premature beat, it's refractory in the ventricle, but it's sensed in the atrium and may actually set off an AV interval with a VP. Now that VP may fall on the T wave of the ventricular premature beat, which obviously is not a good thing. Could be arrhythmogenic. So that's the reason why we usually have it this way around and not that way around. Okay, 24. It's a question of indications, so please answer. Okay, yeah, indications, okay. Right, now the correct answer was this. Oh, yeah, that was the least. Now, all the others are indeed class 2A. Asymptomatic third degree block, class 2A indication, even though it's asymptomatic, it's 2A. Left bundle branch with syncope, left bundle branch block can be considered as being bifascicular block. You have left anterior and left posterior, considered as being bifascicular block. So syncope with a left bundle branch block, class 2A indication. Personally, I go ahead and implant a pacemaker, unless you think it may be tacky, but if that patient has bundle branch block, bifascicular bundle branch block and syncope, go ahead with a pacemaker. Carsten mentioned about these diseases, myotonic dystrophy and so forth. If they have fascicular block, it's also a class 2 indication. Now, asymptomatic Mobitz 2 with bifascicular block is a class 1 indication. It's a class 1 indication. It's in the table with the, I think I've put it here. Here we go. This is chronic bi- and trifascicular block. So right bundle branch block with left anterior block and Mobitz 2 would actually be a class 1 indication. Okay. And the last one, this is really fun. This is why I left it for the last, because I think it's a lot of mathematics there. So go ahead and vote. I'm expecting 25% correct answers on this one. Okay. Oh. So, correct. Done your maths. How do we get that? So, it's mass capacity, ampere hours. Current drain is in amperes here. In microamperes, sorry. So, we have to understand how many hours there are in a year. So, 24 times 365. And then you have the problem with the microamperes and the amperes. And there's a factor of 10 to the power of -6 there. And this is why you'll get 114 and you've got the right answer, which is 6.5. And most of you got that right, so well done. Any questions on the exam? Not bad anyway. Well done. I think you've all done a very good job with the answers. Thank you.